So we're continuing into chapter 3, and again I encourage you to always take a look at the title of the chapter. What's the title of this one? We're interested in the equilibrium of a particle, and one of the great themes was we want to start doing a free body diagram. And again, I pointed out that for this chapter it really all boils down to a point. There's really no motion in the sense of pending motion and of rotational motion. It's just translational. We'll get to moments of the force and then possibility to make it want to rotate. That's next chapter. So we solved it in coplanar and then 3 dimensions. What do I have here? I have a 400-pound crate. So 400-pound crate. It's suspended using a cable with frictionless pulleys. Can you tell me how many frictionless pulleys you see in this illustration? 2 or 3? There's 3. All right. There's one frictionless pulley. There's another frictionless pulley and a frictionless pulley. 2 of the frictionless pulleys are attached to the ceiling or roof or something strong to hold it in place. True? One frictionless pulley is just going along for the ride. It can rotate if you start to pull on them and make the system change its current state. Okay, so how many cables do I have? 1, 2, or 3? Clicker question. How many cables do I have? Do I have 1, answer A, 2, answer B, 3, answer C, 4, answer D. How many cables do I have? I've encouraged you to go ahead and get a thick marker or something, a thick pen, and maybe just start stretching and say, okay, I'm going to trace this cable. Oh, it goes around the pulley. It comes down. Does it end or does it go around this pulley? You know, they could have shown this as a ring with a tension. True? But that's not the way it's shown, is it? This is a continuous cable going around that pulley, up and around that pulley. And how many unique cables do we have?
2.
Hold it. Cables. How many cables do I have?
There's 1 holding the box.
Oh, well, oh, come on. How many people were thinking this is a unique cable right here? Only 1, 2, 3, 4? All right, this group up here, sorry. Yeah, I guess you could vote for B in that case, but maybe I shouldn't grade it, though. But the right answer that I'm looking for is that I really have 1 cable that is going through and around those pulleys. Now, this cable attaching here, let me not grade it, fine. This one coming up, does it go around the pulley or does it go to the middle of the pulley? It goes to the middle of the pulley. All right. So, all right. They show that this T and this T are the same. Is that the same T or should they subscript 1 then T2 on the other side? T1 and T2? They're the same. They're the same. That's right. These are all very big observations. All right, now let's continue on. We have this angle theta, and down here they say that angle is 45 degrees. That angle is 45 degrees. You ready for a clicker question? The tension in the cable is how many pounds? What was the weight of the crate? 400 pounds. So I have to change this to a numeric, and then I'll get started and give you enough time to answer that question. You'll probably need a calculator. All right, so we're in. Okay, how many people actually developed the free body diagram for this problem in order to solve it? More hands should go up. Really, and what should the free body diagram look like? What did you focus on for your free body diagram? Yeah, you could focus right here, the center pulley. And the radius of the pulley is negligible, so it all sort of collapses to a point. And then at this point, then you have something going up here, something going up there, and something coming down there. So you had the weight pulling down, And what did you use for this symbol for this? What? Why not T? Why not T? I asked simple questions. I think T would be fine. Why? Because T was introduced over here. True? All right. Now, I know it's a little bit of, I have two horizontal lines. And this is a theta. What is this angle right here? Trigonometry. No, that's geometry, I even think. Isn't it? Yeah, one of the two. All right, so that angle's theta. So I can decompose this tension into that magnitude lifting. The other component is pulling it horizontally. And so what is this one right here? I'm decomposing it. Is it going to be T times the sine, cosine, or tangent of theta? Take a pick. Sine, cosine, or tangent of theta?
Well, it could be sine or cosine.
As I've gotten, well, it's 45 degrees, so you can make an error and be forgiven. But let's say it was 30 degrees, not 45. Then it would have to be one of the three. True? What will it be? Sine of theta. Now, if I come over and I take a look at this one, I can decompose that one. Hey, you know what? I've got a lifting component from the cable going off to the right as well as the cable going off to the left. True or false? So what's a common error? Leave out off by a factor of 2. And when I see that error, I'll say, they probably only thought one cable was doing the lifting. All right. So when you do this, you find that two cables having tension T, and then we have the sine of the theta component doing the lifting equal to the weight going down. True or false? So that the tension, the tension in the cable is the weight divided by 2 sine of theta, 400 pounds divided by 2 sine of 45 degrees. And what does that come out to be? 283. What do you think 566 is? Ready for a next question? All right. I think I'm going to do this. Before I ask the next question, I'm going to take away some of this information, take away this information, that information, all of this information, take away this information, but you have your notes in front of you. Now we go here. As the angle theta increases, the tension in the cable will increase, remain unchanged, or decrease. What will happen to the tension in the cable as what? As theta increases. It's not an alphanumeric, it's a multiple choice. Let's go ahead and get started. There's plenty of time, I hope. So as theta increases, what happens to the location of the crate? The crate was at this elevation, thinking of Z or Y or something. What happens to the elevation of the crate as theta increases? So it goes from 45 to 50 to 60 to 70 degrees. What happens to the crate? It goes lower. All right. So then it goes like this, down, and goes up. Is that true? Is that what would happen? That's the only way to increase theta, right? You better have a long cable in order to do that, right? You could actually move the pulleys closer together and use the same size cable. Absolutely correct. That's true. The pulleys could be moved together, the top at the ceiling. True? Okay, with that observation, what I'm going to do is I'm going to ask the same question again. And I'm going to ask the question right here. So as theta increases, we now know that the crate goes down. You better have a long cable, or you could view it as the pulleys on the top getting closer and closer together. Both of those conceptually work. But I'd like to get closer to 100% correct in the class. Okay? So, same question. Go for it. All right, so I do hope that extra time and a little extra discussion moved us closer to being, as a class, more correct. So why is it that when the angle theta increases, the crate's further down, the cables have to be longer or the top pulleys closer together, why does the tension in the cable go down? Why does it decrease? Somebody who got it correct. Why does it decrease?
It'll decrease all the way until you get 90-degree angles in which each cable will hold 200 pounds.
So in the extreme, he's thinking I have a cable going straight down, which has a theta of 90 degrees, and another cable going straight down, another theta of 90 degrees, holding the weight. And now those are just pulling straight up. And this is the 400 pounds. And guess what? This is 200. Does that help a little bit? Okay. The math will show it too. The math will show it. Let's take a look at how we were before. So we were 2/3 correct as a class, and we moved it to 90% correct as a class. All right. Should I grade this other one? It was a fair question. Let's grade it. Move on. We haven't left this problem yet, have we? You ready for another question? Multiple choice. If the 400-pound crate is suspended using the cable and frictionless pulleys, what is the minimum possible tension in the cable? 0, 200, 400, 800. It cannot be determined. All right, so let's take a look at this. Didn't I just give you the answer?
Yeah.
So I went too far in my explanation. I didn't intend to go that far. But it's 200 pounds. That's the answer that we got. Okay, 82%. Why are we not closer to 100? I don't know. Well, here's another question. This never ends, does it? Same thing. What is the maximum possible tension in the cable? Either 0 pounds, 200, 400, 800, or I think there's another one right below it. Put E. Cannot be determined. All right. So you have the same problem, same responses. What is now not the minimum, what is the maximum possible tension in the cable? All right, everybody in? So before, when theta went all the way to 90 degrees, okay, you have to have extremely long cable, or you move the cables, the pulleys together at the top. That's probably the easiest way to do it. We found that you had the minimum tension in the cables, or the cable, one cable. Okay. Well, do you think the other extreme is? So what happens if I pull, and now I get thetas very, very close to 0, right? So if I do a free body diagram and I'm close to 0, is this angle right here still theta? If I actually go theta equal to 0, do the two tensions forces acting on the particle do any lifting? Nope. Even though you need to support a lot of weight. True? You would have to really have a high tension on that. It's not just going to be 800 pounds. It could be a lot more. And you can break things that way. Okay, I didn't do so well on that, did I? All right, well, let's try and press forward. I donated blood the other day. And every time I donate blood, they ask me questions like, are you healthy? Are you on prescriptions or taking drugs or done all these things? Have you eaten a full meal in the last so many hours? And then they ask a question. This is it. It's not a clicker question or anything. They say, how tall are you and how much do you weigh today? And I give an answer. And if I went around this room and I found some people that grew up probably in Mexico or Canada or some other, they would give an answer different than if you were born and raised in San Antonio or Houston or Texas. You ever notice that? So you may say, oh, I'm so many centimeters tall instead of so many feet and inches. How many people, I'm just curious, they would say, I'm going to give you my weight in kilos. Yeah, one, that's all. But more of us probably will be doing that in the future, and not pounds, right? But the next problem, we'll use this type of information, because if I say, what is your weight? And you say, I'm about 64 kilograms. All right? First of all, that doesn't click to me. It doesn't register to me, and I've got to convert that to pounds. The other thing is that a good unit of weight, kilogram? No, you would just beat up. You just went all through this pure engineering education and newtons or units of force, and weight is a force. Don't confuse mass with weight. Don't confuse mass with force. They're different. But guess what? When you get out there, you'll find that a lot of times they'll talk about forces, slang. Just like they'll talk about weight in slang, they'll call it kilogram. They call it kilogram. And so it's like, what do you want to buy? 1 kilo or 1 kilo? I mean, it just they don't put it on a scale and measure its weight in newtons. They put it on and they say, oh, I got a mass balance scale and I sell it in kilos. Or I put my body on a scale and I balance it and I tell you my mass, but they say weight in kilos. All right, let's go and solve this problem. I have a 50 kilogram crate. It's supported with cables. So I have, now is this at D and C and B and at A. Are any of those pulleys as I've shown them? What would you call these? They're just rings or supports. So D is not a pulley. But what's between D and C is a cable. True? All right. So they say determine the tension in each cable. How many unique tensions am I going to calculate? How many unique cables do I have? Do I have clicker question A, B, C, D, E? Do I have 1, 2, 3, 4, 5? And yes, we will count this one. Yes, count that one as a possible cable. So no ambiguity on that. All right, so let's go ahead. If you like, you can color code them. I like to do that, especially when you're brand new. Let's say this is a red cable, that's 1. Then we'll just jump over to purple cable, 2. Jump over to a green cable, 3. Jump over to a blue cable, 4. Jump over to, I don't know, some darker cable, 5. Is there 5 cables? Let's grade it. Hey. Should we solve for A's or B's or T's or F's with some subscripts? You know, this is just trying to figure out what am I solving for? I'm solving for tensions in cables. Maybe you want to solve for the tension in A to B, and then maybe tension B to D, and tension B to C, and tension C to D, and tension, so D to the crate. Some subscripts. So I've clearly identified the 5 unknowns that I want to solve for. You say, isn't that kind of trivial? I think a lot of students don't quite understand what they're trying to solve for when they start solving problems, especially in statics. They get confused. Maybe not this early in the semester, but maybe in a couple more weeks the class will get a little more intense. And then you need to be clear. This is what anticipated units would I solve for the tension in each of these cables? Newton, kilonewton, or kgf. Kilogram force. Kilogram force? Well, let's take the easiest one. This one going right here down to the crate. All right, if that crate has a mass of 50 kilograms, its weight is also 50 kilogram F, kilogram force. Sometimes they even just leave off that subscript F. I know it's a little bit of a slang, but it's very, very, very common in the world. Got it? So they talk about the tension being 50 kilogram force. So guess what? There's the answer for part, let's call it tension down to the crate, or here. Tension from D to the crate. 50 kgf. How do you like that? Box it, call it quits. How do we do that? Got 1/5 of the problem. 20%. Hey, I'm almost there, right? We did a free body diagram around the crate. All right. Yes. Well, the crate is 50 kilograms. Okay, then you're going to convert it to newtons. Just like we had LBM and LBF. And in this book, it's just look at. It's LB. Look at the context. Is you talking mass? If you're talking force? And believe me, the same thing happens in Mexico, Canada, Europe, all over the world, SI. They just don't emphasize it in textbooks. It's kilograms. Unless you're moving off the surface of the earth, it's a kilogram weight. Yep. Okay, since you're the only one that raised your hand. Anybody else, if I said, tell me what is your weight, you would actually give it to me in kilos. Only one person in this room of about 60, 70 people. I would normally expect more, okay? Do you know your weight in newtons? No. You know it in kilos, don't you? There you go. Go find a friend from Mexico that only, is thinking centimeters and kilos, and ask them, what's your weight? And then they're going to tell you kilos. You say, no. I want it newtons. They're going to stare at you. They're really going to stare at you. They're going to be like, huh? I'm telling you. Add 0 is close. 9.81 is close to 10. You're right. But actually, most of them will struggle. They'll be like, well, like this morning, before I ate breakfast and before I had a cup of coffee, I was, They sometimes know it down to two significant digits on the sometimes even 3. All right. Very rarely 3. All right. So let's do this. I'm going to walk around the room. I want you to give me as many of these other 4 as you can. And I'm going to pass out a sheet of paper for you. So we have to solve for 4 unknowns. Mathematically, if I have to solve for 4 unknowns, how many independent equations should I have, regardless if they're algebraic, nonlinear, or linear equations? How many equations should I have? Don't chase your tail. Don't try and solve for 4 unknowns with 2 equations. I need 4 equations. All right. Now, we're doing 2D equilibrium. Now, if you do an equilibrium with this ring, D, you cut it right here. Free it. Free it from what? The rest of the surroundings, the world. You focus on that study. You need to draw off of the diagram an independent free body diagram for ring D. And it doesn't have to have superfluous stuff in it. All right, so I would put a dot right there, and I would say, free body diagram. I don't have to spell it out. I know what I'm doing. You know what you're doing. FBD, you get tired. You get the little acronym for this class. For ring D. You have to be clear exactly what it is. Now, when I cut right here, what do I just cut through? A cable. What's the surroundings going to do to the inside? It's going to exert you're going to say, this is so trivial, Professor. It's going to exert a force. We put forces on free body diagrams. Somebody just put this. That's a line. That's not a force. A force has not only that, it has that. What's that tell you? The direction. The direction. Somebody else they had this line, they had this line, they had this line, they had this line, they had this block. Is that a free body diagram? No, it's not. It is not a free body diagram. Superfluous stuff. This is a force, not a line. This is a force, not a line. And this is a force you cut right there. Hey, we already found the tension in that cable. Sure. So you can say this is W is equal to 50 kgf, or just dispense with the subscript F. We're talking kilogram force. Think about it. Put F in there. Okay, fine. Now, label your free body diagram. This is the tension going from B to D. This is the tension from C to D. Now, you may want to say, well, is that the same as the tension from D to C? The order of the subscripts is not that important. Maybe you put the first letter first and the higher letter second, But some syntax, some notation on it. And then in the free body diagram, maybe I come in and I put in some angles. Can you see that that's 30 degrees? Sure. You get good at this. So you see that's 45 degrees? Sure. I think I have a pretty good free body diagram of what? Ring D. All right. I'm now going to do the equilibriums. I know that the sum of the forces equal to 0 is a vector equation, but we boil it down to sum of the forces in the x direction and in the y direction. Maybe you go ahead. We're not going to be changing it up. Again, this is pretty common. X is horizontal, y is vertical. You could put your coordinate system in. Maybe that's helpful. But maybe you just know that. Let's continue on. So in the x direction, does the weight have any contribution in the x direction? Purely in the y. And it's in a negative y. So what we're going to find is the tension in the cable B to D times the cosine of 45 degrees that picks off that x horizontal component must equal, going in the opposite direction, in the positive x direction, the tension in the cable C to D times the cosine of 30 degrees. Maybe you needed to put, sum of one of them negative equal to 0. That's fine. But after you've done this a little bit, and I'm fighting for space because I don't want to scroll down here, okay? This is pretty good. Is this okay? I look at that equation. How many unknowns? 2. I have this one, B to D, and I have C to D. Those two are unknowns in that equation. I need another equation, the sum of the forces in the y. You're going to say, Professor, you're belaboring this point. Why can't we just write the answer down? I'm not that smart, and I suspect you're not that smart. All right, in the y, we're going to have the tension B to D times the sine of 45 plus the tension C to D times the sine of 30. Both of those are lifting, pulling up, and it's equal to the weight going down. Now at this point, you can just forget that you're an engineer, think about being a mathematician. I have 2 equations, 2 unknowns. 2 equations, 2 unknowns. Somebody showed me their calculator, said this calculator can whoop up on this problem. All I have to do is input the matrix like that. Is that calculator approved for the exam? Yeah, it is. Maybe you want to learn all the capabilities of your calculator. All right? So, learn what your calculator can do and get good at it. Set it up in matrix form. Or take this first equation, eliminate one of the unknowns. I think somebody went like this. Let's eliminate TBD, which would be TCD times the cosine of 30 degrees divided by the cosine of 45. That's from this equation. Then I substitute into there to the second equation. I then have equation only in terms of CD, tension C to D, which is going to be cosine 30 times the sine of 45 over the cosine of 45 plus the sine of 30, all of that equal to W. Did I do the math correctly? Thumbs up if you agree. Couple thumbs up. Couple more. Good. At this point, I would do something like this. I'm solving for tension C to D. I'd put in the weight. It's a 50 kilograms force. I do the cosine 30. Is that the tangent, sine over cosine? 45 plus the sine of 30. And then I finally put tension C to D. What is that answer, please? 36.6. 36.6, 36.6, 36.6. Anybody else? Now, what do? You go back to that other equation, which would be TBD is equal to this equation right here. I know I've got a lot of arrows, but it's 36.6 times the cosine of 30 divided by the cosine of 45. And the tension B to D is 44.8 kgf. Somebody says, I really want to work in newtons. Multiply everything by 9.81. Call it a newton. I mean, at this point, it's either way, right? Two of them down. But we only used one free body diagram. We have to go and get another free body diagram. Guess what I'm going to do? I'm going to say you'd use this free body diagram right here. Why do I circle it with this little dashed line? This is the focus of the study. I have to now cut through 3 cables. One cable is going to be pulling down, one cable pulling horizontal, one cable pulling up. Draw the free body diagram. Get everything correct on it. In the interest of time, I'm going to have to move on, okay? I've got another problem to solve. All right? All right. I want to solve now a 3D problem, because you have to move into 3D, and this is where typically students wipe out, because they're going to have to trust their math a lot more than 2D. So we have a force of 75 kilonewtons. Here's this force right down here. Let's take a look at our coordinate system. Here is positive x. Here is positive y. Here is positive z. It's a good coordinate system. And F, if I look at it, F looks like it's completely only along one axis. And it is. It's only along the y-axis. So I can represent that force as a single, vector, three-dimensional Cartesian vector. It would be 0 in the I. It would be 75 in the J. It would be 0 in the K. And it's units of kilonewton. Does it look pretty good the way I've represented it? You like that notation? Good. All right. It holds a 100 kilonewton crate. Okay, they didn't give me the mass. They gave me the actual weight of this crate. Here is the crate. And what do you think this line going down from the ring is? Is it aligned with one of the axes? It's aligned with the z-axis. My guess is, and that's the way the whole book has been, g is down in the negative z. So could I express that weight as a three-dimensional Cartesian vector? Would it be anything in the I? No. Anything in the j? No. But it would be negative 100 in the k, and it would be units of kilonewton. Does that look okay? How do you know it's this negative sign, Professor? It's just pretty obvious. I mean, gravity's, the way the crate's hanging, it's being supported by the ring. This little cable is in tension. And there you go. All right. All right. 2 ropes are pinned at C and at B. 2 cables or ropes. They come out and they attach to this ring at A. Is that a pulley or a ring? There's a big difference. All right. Now, they tell us the tension is the same in each of them, so the tension here is 140 kilonewton, and this one's 140 kilonewton. Okay. Calculate y and x, which are the coordinates of point A. So point A is located at 0 in the x. Here's point A. Is it 0 in the x? Can you see that? And then it's y in the y. So it's how much distance out from the origin in the y direction. And then up z. And that's the location of point A, the ring. What's happened at the ring? Well, F connects to it. The tension in the cable going back to B, the tension in the cable going back to C, and then we have the tension in the cable going down to the crate. All right. So how will I solve for the two unknowns, y and x? And they're geometry. They're not forces. They're just where it's located. Where is the ring located? How would you do it? Did I say x? It needs to be z. Thank you. It needs to be z. All right? How do I solve for y and z? The theme of the whole chapter. We're studying statics. We're looking for a particle. We're going to do the equilibrium of a particle. The particle can now reside in 3D. Now, whenever you get to 3D, it's really hard to generate a decent 3D free body diagram. But I encourage you to try it once or twice in your life. Here it is, and then we're going to have a tension, and a tension, and a weight, and a force. And we know what this is. That's F, already described. The weight, already described. And now I have to have this tension going back to B and the tension going back to C. How am I going to get those as vectors? I know their magnitude of the tension is 140. So help me get the tension in B. Tension in B. How do I calculate that as a vector? What I would do is I would multiply by the magnitude, and I'm going to just put TB, and that magnitude of the tension is 140. But I'm going to leave it as a symbol for right now. 140 kilonewton times something which is a vector which gives me the right direction. And I put a little u there. What is that u for? Unit vector. Where does the unit vector go from to? It goes from point A toward point B. So, how am I going to get the unit vector from A to B? You're going to get a displacement vector from A to B and divide by the magnitude of that displacement vector from A to B. Won't that give you a good unit vector? True? All right. Now, you can do this R A to B in a couple steps. Like, would it not be RB minus RA? And I encourage you to make sure you're confident. But what will be the change in X going from A to B? Go slow here. What is going to be the change in the X going from A to B? Is it going to be plus 5 or negative 5? Negative 5. How about in the J? Is it going to be plus something, minus something? From A to B, it'll be minus Y. And then the really hard one. What about the Z? K. You're going to start at Z and you're going to end at 4. You're going to end at 4. You're going from A to B. You're going to start at Z and you're going to end at 4. 4 minus Z plus. Let me try and clean it up just a little bit. This is I. Now, I did that fast. I'm looking at the clock. I'm running out of time again. But you have to be able to do that, okay? Now, can you tell me the magnitude of RA to B? No, this is just displacement vector. Once I get it, I get a unit vector, then I multiply by the magnitude 140 kilonewton, and I have a good representation of a three-dimensional tension force acting on ring at A. That's exactly right. Square root 5 squared plus y squared plus 4 minus z quantity squared. There's no obvious way of simplifying that to make it any better for us in the future on this problem. We're just stuck with some expression like this, which is not so nice. But there it is. Can you do the same thing over here from A to C? All right, let's do that. I'll scroll down. What is the displacement from A to C? What is my change in the I? Plus 5, exactly. How about in the J? Minus y. I know some people are really fast at this and good. Some are you're like, but you need to. And then how about for the K? 4 minus z again. And then just make sure and look at it and make sure you're right. And then the magnitude of A to C is the square root 5 squared plus y squared plus 4 minus z squared. Let me ask this. Are these two magnitudes the same? Regardless of what y or z is? You're exactly right. They are the same. All right. So I can basically get a three-dimensional vector for the tension to going to C and then the tension going to B. I have the force being applied as a three-dimensional vector and the weight being applied as three-dimensional vector. What is our equilibrium condition? So we have the sum of the forces equal to zero force. And so we always take that vector equation and we bust it into the x direction, the y direction, and the z direction. And you get three scalar equations from that one vector equation. So in the x, this is a little, should I pause and let you write it out? I know that I had to scroll down, so I don't like that. In the x, okay, this is the x direction, going that way. Is F anything in the x? Is the weight anything in the x? No. You're only going to have two players in the x. The tension going to C and the tension in the cable going to B. So what you pick up is you pick up the tension in the cable going off to C times that component, which was 5 divided by, and I'm going to call this length. What do you mean length? Just call this length. I'm tired of writing square root of 5 squared plus y squared plus 4 minus z squared. So you just call this length, L. And then you're going to have minus the tension going off to B, not D, B, times 5 divided by L is equal to 0. Each of those had the same tension, true? So these can cancel. The 5s cancel. The length is equal to the length. Really, what that x equation does is it confirms that for this setup, both of those cables have to have the same tension. You can't have one with a different tension than the other. It wouldn't be an equilibrium in the x. All right, let's press forward. How about for the y? From the y direction, you're going to have the tension in the cable C, which does a lifting of hold it, this is a y direction. Get your y down this way. I'm not doing the lift yet. That's in the z. So they're going to be pulling back each of those cables. Tension in C times y divided by L plus the tension in B, y divided by L, and that's equal to the force F pulling forward. Look okay for equilibrium equation in the y? Well, you could do this. You could put negative, negative, plus equals 0. That's the same equation. All right. And then in the Z, we're going to have the tension in the C. And you have a lift, which is 4 minus Z divided by L. You're going to have the tension in the B, which is the same. 4 minus Z divided by L. And down, you have the weight of the crate. All right, this life was easy up to this point because where are my unknowns? What are my unknowns? Well, take a look. I can rewrite maybe this equation right here. And so the two tensions are the same, so let's just call tension times 2 times 4 minus Z divided by, and I'll bust out what L is, 5 squared plus Y squared plus 4 minus Z squared, all that square root. That's equal to the weight. I know the weight, I know the tension, I do not know Z, and I do not know Y. We can take our other equation, and what do we have? We have 2 times the tension, which we know, times Y divided by the square root, 5 squared plus Y squared plus 4 minus Z squared, equal to the F being applied. Again, this equation, I have known, but I don't know the Y and I don't know the Z. 2 equations, 2 unknowns. How would you solve for it? There are two things that I'll just say. One is if your calculator can help, try to see if it can help. You can handle 2 equations, 2 unknowns, but they're linear algebraic equations. Are these 2 equations linear algebraic? Oh, they're algebraic equations, but are they linear? They're not linear because you have the Y squared and the 4 minus Z squared. So, if they can't do it with a calculator, or your calculator doesn't know how to do it, what's your other strategy? It's insightful algebraic manipulation. Meaning every one of these nonlinear algebraic problems are slightly different, and you go down a slightly different path. But if they're all linear algebraic, oh, you set it up as A, matrix A times unknown X is equal to the vector right-hand side B, AX equal B. Maybe if it's small, use Cramer's rule. Great, easy pattern. But when they're nonlinear algebraic equations, it's a little more challenging. How would I do it? By, some unique manipulation, algebraic manipulation. How would I possibly do it? Well, I know that I had this L under here. What I could do is I could take this equation here. I know this gets nasty, but you would say, okay, I'm going to have L is equal to 2t times 4 minus Z divided by W. Thinking that this is L, right? Take and substitute that into this equation. So I have 2t times Y divided by L. Hey, but L is 2t 4 minus Z times W is equal to F. All right, there is no one unique path. Those cancel. And I get that F, known, weight, known, but I still have unknown Y and unknown Z. So, but there's not an easy way to solve it. Believe me, this would be a very challenging problem on an exam, but you would almost be graded on the process more than the final result in being clear and setting it up, because I really throw this out to you. This is correct, and this is correct. See if your calculator can help you. Now, if you're on an exam and you could set it up and you know anything about Excel, which you can't use on an exam, then this is one way of solving it, okay? And it comes in that to satisfy my equations, I need to get z about 2 and y about 1.5. But there's another one. How many people ever use this one? Wolfram. 1, 2, 3. Perfect. That's quite a few for this class. It's free online, and it can do some really powerful math. And so you just say, okay, solve this problem. And the way I did it was I said, let's just let t be a variable, tension, 140 given, comma. That means given the equation. Then w is equal to 100, what is that? Comma. Another equation, so I'm kind of like defining my variables. F 75, comma. And then what do you see right here? All of that. That's my equation for one of the x or y balance equations. Not the x, y or z balance equation. And then this one, comma, is the other one. And then it goes back and says, is this what you intended? Is this what you intended to solve? And if it is, here's your solution for y. Oh, by the way, it worked it out, can you believe it, analytically to some 25 divided by 3 square root of what, 31? I couldn't, I didn't. Or z, here it is, worked out to, which is about 2. You don't have to use it that way in Wolfram. Here's another way I did, like, I think I mistyped or solved D, distance instead of L, and then this. Anyway, you come up with y of 1.49 and z of 2. So I know the answer, solved it multiple ways, but I don't know an easy way for you to solve it analytically with your little calculator. So if you're given a problem like this, you're not going to be graded heavily on the final answer. It'd be like setting it up and working through it clearly. Make sense? All right. Sorry about that. I wanted to give you more time to solve that problem. But at this point, I'm going to call it quits, and I'll see you next time.